So good evening, ME250. This is Professor Jones. I have a corner of my living room set up as a temporary lab. So I'm going to try to walk you through what we would have done with the non-destructive evaluation lab. Okay, let me show you our experimental setup. This is an old-fashioned oscilloscope. We used these when I was in school. So we're going to be looking at the time of travel of an ultrasonic wave going through several different kinds of samples. And I'm not sure that I can film that and do the test at the same time. So I might be taking some still photos of what's going on. Oh yes, and we have our laboratory assistant here too. So our ultrasonic signal is generated by this pulsar receiver unit. Okay. And that's hooked to our oscilloscope. And what we're actually using to inspect our samples is an ultrasonic transducer. And there are two kinds of these that we use in this lab. One of them generates a plane wave, and the other one generates a shear wave. So to use these, just as you saw in the video, we're going to put a couple drops of an ultrasonic couplant on our sample. In this case, it's propylene glycol. Okay. Sorry, trying to do and photograph at the same time. Okay. So this cylindrical sample here happens to be brass. Emmett, move. Okay. So I'm going to take my transducer, and I need the couplant to get an efficient transfer of energy from the ultrasonic transducer, which has a piezoelectric crystal in it, into the sample. Okay. I'm not seeing anything on the waveform. And that's because I didn't turn on my signal unit. This has two switches in the back, and I got the wrong one yesterday, and I did it again. Okay, let's try that again. Okay, so now on the oscilloscope you can see it's picking up the incoming signal. So, if I haven't managed to make you seasick on these videos before, this one will. Okay, so now I'm pressing this transducer over the couplant. Okay. Whoop. And I need to take a second and figure out the time scale I need on this oscilloscope to be able to show you the rebounded wave. No, Emmett, propylene glycol is not good for you. Okay, I'm going to pause this and pick up the video in a separate video in a minute. Okay, so what I had to do was adjust on the horizontal position on our oscilloscope output. I can set a different number of microseconds per division. And when we're talking per division, that's per each one of those squares. Sorry, guys. Okay, so let's see if I can get this to work now. Okay, so if I take the probe off the sample, you just see the incoming pulse. It's not being rebounded by the bottom of our sample. When I press this onto the sample, now you can see the sound wave peak as it's returning to the transducer. Okay, so that looks like it's just under 5 squares in time. So I'll have to look and see what our time setting is so that we can figure out what the actual travel time is corresponding to those 5 squares. Okay. So if I change samples, I also have an aluminum sample here. Let's see if we can get a signal off of that. So let me show you the aluminum sample. You guys have seen these. These are our compact tension samples. Holy cow, look at all the peaks on that one. So what we're picking up here is the sound wave actually rebounding multiple times and coming back to the transducer. So I probably need to change my time axis to be able to get a more accurate reading of an individual rebound on that. Okay guys, I'm going to take another try at that aluminum sample. So I've changed my number of microseconds per big square on the oscilloscope. Okay, so now I have from the beginning of our incoming peak, 1, 2, 3, 4, 5, about 5.5 squares. Okay. So this is also a different dimension than the brass sample is. So I have to figure out my total travel distance, which is down and back. Okay, it goes from the top surface of the sample all the way through the sample, rebounds off the back surface, and comes back to my transducer. Okay, now I've got the compact tension sample made out of steel under the probe. So the aluminum sample of the same geometry was giving us a back wall signal of around, say, 5.5 squares in time. And I haven't changed the horizontal time scale at all on this one. So our steel is taking a little bit longer for the sound to return to the transducer. It looks like a full, really close to a full 6 squares. Okay. Now, next I want to show you a piece of aluminum that has a little tiny hole in it. Okay guys, here's our aluminum block. It has a little hole drilled in it, about 3/4 of the way through the thickness. Okay, so I'm going to start with the transducer on the right end away from the hole, and I'm going to slide it along, and we'll see where we pick up the reflection from the hole. Okay, so I'm sliding just right to left along this aluminum block. Sorry for the jiggling, I got to switch hands to do this. Okay, and not put my hands over the lens. Okay, so here's our incoming pulse. Here's where we are away from the hole. Okay, now as I slide along, now I'm about midpoint. Oh, that must be the hole showing up. Did you see the difference? Here at about 3.5 squares in time, I get the reflected signal from the underside of the sample. If you look in the middle of those three, see that peak? That's a signal reflecting off the hole. And as I get closer and closer to the hole, I get a bigger and bigger signal. Now if I slide top to bottom, that hole's in the middle of my sample. There it is, goes away. I'm at the top, center, bottom. Okay, I think that's everything I needed to show you for the lab today. Thanks for hanging in there with me. Hope you're not seasick. Bye.